3.5 billion years ago, Mars was alive with liquid water. Rivers carved channels across its surface. Lakes pooled in ancient craters. Rain may have fallen on a world that looked more like early Earth than the frozen, rust-colored desert it is today. And somewhere in that ancient, wet, chemically rich environment, something happened. Scientists have spent decades trying to find out what. And in April 2026, 2 separate NASA rovers from 2 different locations on the Martian surface handed humanity the most compelling chemical evidence ever gathered, that the building blocks of life were not just present on ancient Mars, but were preserved inside its rocks for billions of years, waiting to be found. On April 21st, 2026, a paper published in the journal Nature Communications announced something that stopped planetary scientists in their tracks. NASA's Curiosity rover, which has been crawling across the floor of Jezero Crater since 2012, had detected more than 20 distinct organic molecules inside a 3.5 billion-year-old Martian rock, using a chemistry experiment that had never been performed on any world other than Earth. The experiment worked. The molecules were there, and the scientific community immediately erupted into a debate that touches the deepest question human beings have ever asked about the universe. Are we alone? To understand what NASA found, you first need to understand what organic molecules actually are and why finding them matters so much. The word organic does not mean alive. It does not mean biological. In chemistry, organic simply means carbon-based. Molecules built around chains or rings of carbon atoms, often bonded with hydrogen, oxygen, nitrogen, and sulfur. The reason organic molecules are important in the search for life is that all known life in the universe, everything we have ever studied, from bacteria to blue whales, is built from organic chemistry. DNA, proteins, cell membranes, the energy transfer molecules that power metabolism, the amino acids that construct every living thing, all of it is organic chemistry. So when scientists find diverse, complex organic molecules in ancient rocks on another planet, they are not proving life existed there, but they are proving that the raw ingredients were present. And that is a very different situation from finding nothing at all. The experiment that made this discovery possible is called the SAM-TMA experiment. SAM stands for Sample Analysis at Mars, the instrument suite inside Curiosity that has been responsible for the most important chemical discoveries of the mission. TMA stands for tetramethylammonium hydroxide, a chemical reagent that the instrument used to break apart and release organic compounds locked inside Martian rock. This wet chemistry approach had never been used on another planet before. On Earth, it is a standard laboratory technique for liberating complex organic molecules from solid samples. The fact that it worked on Mars, in the harsh, radiation-soaked, frigid environment of Jezero Crater, was itself a milestone. The fact that it revealed more than 20 different organic molecules in a single rock sample made it one of the most significant analytical results in the history of Mars exploration. The molecules Curiosity detected were not simple. They were not just single carbon atoms floating loosely in a mineral matrix. They included benzothiophenone, a 2-ring aromatic molecule containing both carbon and sulfur that has also been found inside meteorites and asteroids, making its appearance on Mars a discovery that connects the chemistry of Mars to the broader chemistry of the early solar system. They included naphthalene, confirmed for the first time as indigenous to Mars. They included nitrogen-bearing organic compounds. And nitrogen is critical because it is a building block of amino acids. And amino acids are the foundation of proteins. And proteins are the machinery of life. Lead researcher Amy Williams, a professor of geological sciences at the University of Florida and a member of both the Curiosity and Perseverance science teams, described the significance plainly. She said the team believes they are looking at organic matter that has been preserved on Mars for 3.5 billion years. She said it is useful to have evidence that ancient organic matter is preserved, because that is how you assess whether an environment could have been habitable. And she said that if you want to search for evidence of life in the form of preserved organic carbon, this experiment demonstrates it is possible. The rocks that yielded these molecules came from a region of Jezero Crater called Glen Torridon, specifically from a geological layer called the Knockfarrell Hill member. Curiosity collected these rock samples during drilling operations in 2020, but the full chemical analysis required years of data processing and instrument work before the Nature Communications paper could be published. Glen Torridon is a clay-bearing region, and clay minerals matter enormously in this story. Clays form when water reacts chemically with rock over long periods of time. They are excellent at trapping and preserving organic molecules within their layered crystal structures, protecting those molecules from the radiation and oxidation that would otherwise destroy them over billions of years. The fact that Curiosity found more than 20 organic molecules in clay-bearing rock that was deposited at the bottom of an ancient lake environment is not a coincidence. It is a confirmation of something scientists have long suspected. Mars preserved its organic chemistry in exactly the places where water was most abundant and most persistent in its ancient past. But Curiosity's April 2026 announcement was not the only major Mars discovery in the months surrounding it. 7 months earlier, in September 2025, NASA's Perseverance rover, which has been exploring Jezero Crater since landing in February 2021, generated headlines that were even harder to explain with non-biological chemistry. Perseverance found a rock called Cheyava Falls in the Bright Angel Formation near the ancient dried-up Neretva Vallis River Valley, an arrowhead-shaped specimen roughly 3 feet by 2 feet. When the rover's instruments examined the freshly abraded surface of that rock, they found something that no one had seen before on Mars, a distinctive pattern of mineral rings arranged in what scientists immediately recognized as leopard spots. Those leopard spots were not a visual curiosity, they were a chemical fingerprint. The spots consisted of iron-bearing minerals, vivianite and greigate, arranged in precise rings around cores of organic carbon, embedded in clay-rich mudstone that formed at the bottom of an ancient lake bed approximately 3.5 billion years ago. On Earth, exactly this kind of mineral pattern, iron minerals, forming rings around organic carbon in ancient sedimentary rock, is one of the textbook signatures of microbial activity. When microbes die and decompose in certain low-oxygen aquatic environments, their organic remains create local chemical gradients that draw in iron from the surrounding rock, forming precisely this kind of concentric mineral halo around the decaying organic material. The pattern is called a biosignature because biology is the most straightforward explanation for why it forms. It does not prove life. Geochemical processes can theoretically produce similar patterns, but it looks like the kind of thing life makes, and it looks exactly like what you would expect to find if ancient microbes had once lived, died, and been preserved in the mudstone of an ancient Martian lake. The paper describing the Cheyava Falls findings was published in the journal Nature in September 2025, one of the most prestigious scientific publications in the world, with an author list spanning scientists from NASA, the SETI Institute, Purdue University, and institutions across Europe. The paper was careful and deliberate in its language. It presented both biological and non-biological explanations for the observations and stated that both remained plausible. But it also said clearly that the evidence pointed to an ancient environment that was chemically similar to environments on early Earth that we know supported microbial life. Natalie Cabral of the SETI Institute, one of the most prominent scientists in the field of Mars astrobiology, described the Cheyava Falls discovery as the most robust case so far for further investigation. She said that whether the data pointed to ancient microbes or to unusual chemistry, either outcome was significant, because one would deepen our understanding of Mars as a geologically complex world, and the other would change our understanding of how many worlds in our solar system life could have emerged on. Then came another paper, published March 31st, 2026, also in Nature Communications, this time from a team led by researchers at Purdue University analyzing data from Perseverance. This study focused on unusually high concentrations of nickel found in rocks along the ancient Neretva Vallis River Valley. The nickel detections were made using SuperCam, one of Perseverance's primary science instruments, which fires a laser at rock surfaces and analyzes the light produced to identify chemical elements. What the team found was that the nickel-rich zones in the Martian rock were concentrated in exactly the same areas where organic carbon and reduced sulfur had already been detected, a combination of 3 elements that, on Earth, is associated with some of the oldest known microbial metabolisms, some of the most ancient bacteria on our planet, generate energy by oxidizing nickel and sulfur compounds in a process called chemolithotrophy. These bacteria do not need sunlight. They do not need oxygen. They live in environments that most life cannot tolerate. Deep ocean vents, subsurface rock formations, ancient lake sediments, and they leave behind a chemical signature that looks like what Perseverance has now found at Neretva Vallis. Henry Manelsky, the lead author of the nickel study and a former doctoral candidate at Purdue, described the discovery carefully but directly. He said that the nickel-rich areas also contained organic carbon and patches of reduced sulfur, previously described as a potential biosignature. He said that together, these findings support the hypothesis that the right chemical conditions, and even some of the building blocks for life, likely existed on Mars billions of years ago. Ashwin Vasavada, Curiosity's project scientist at NASA's Jet Propulsion Laboratory, perhaps captured the cumulative weight of all these discoveries best when he said that the revelation of the mission to him had been not just that Mars was habitable, but how amazingly habitable it was. He said that seeing a diversity of organics meant they were sensing the tip of the iceberg of a greater diversity that once existed there. And then he said something that revealed exactly how much is at stake in the decisions NASA faces right now. He said, "I want the story to finish." The story he is referring to is Mars Sample Return, the mission that scientists on every Mars program in the world agree is the single most important next step for answering the question of whether Mars ever harbored life. The Perseverance rover has been collecting rock cores since its landing in 2021. It has drilled into mudstones, river delta sediments, ancient lakebed formations, and carbonate-rich rocks along the Martian unit, the ancient shoreline of Jezero's lake. Many of these samples are sealed in titanium tubes and cached on the Martian surface, waiting to be picked up by a future mission and returned to Earth. The samples are extraordinary. They come from environments where organic molecules have been preserved, where biosignature minerals have been detected, where the chemical conditions for life were demonstrably present 3.5 billion years ago. Getting those samples into terrestrial laboratories, where scientists can perform isotope analysis, nanoscale imaging, and the full range of biochemical tests that are impossible on a rover, is the only way to answer definitively whether what the rovers have been detecting is evidence of ancient life or the result of purely geological and meteoritic processes. But Mars sample return is in trouble. Congress canceled the ambitious and expensive joint NASA-ESA plan for a sample return mission in January 2026, following years of cost overruns and schedule delays. NASA's Perseverance rover has already collected the samples. They are sitting on Mars. The mission to bring them back does not currently exist in any funded, approved form. Scientists have not stopped arguing for it. Vasavada's statement, "I want the story to finish," is not just a scientist expressing curiosity. It is a scientist watching the most important planetary science mission in a generation hang in political limbo while the evidence accumulates and the question remains unanswered. The significance of what these rovers have found in the last 8 months cannot be measured only in technical terms. It has to be measured in the context of everything humanity has been trying to learn about Mars since the first spacecraft flew past it in the 1960s. The Viking landers in 1976 performed the first life detection experiments on Martian soil and returned results that scientists have debated ever since, results that some researchers believe pointed toward chemical reactivity and others believe may have detected trace metabolic activity, but that were never definitively resolved either way. Orbiters have detected methane plumes that flare and fade in patterns that some scientists interpret as evidence of geological or biological activity in the subsurface. The Spirit and Opportunity rovers found evidence of ancient water environments. Curiosity confirmed that Jezero Crater was once a habitable lake environment for millions of years. And now, in 2025 and 2026, 3 separate published studies in 2 of the world's most respected scientific journals have documented organic molecules, potential biosignature minerals, and the chemical precursors of life preserved in ancient Martian rock at 2 different locations on the planet. None of this proves life. Scientists will say that every time the topic comes up, because that is what the evidence currently demands in terms of honest communication. The organic molecules could have arrived on meteorites. The leopard spot mineral patterns could have formed through purely chemical precipitation processes. The nickel-sulfur organic carbon combination could reflect ancient hydrothermal activity rather than biology. The experiments conducted on Mars cannot distinguish between these possibilities. Only Earth-based laboratory analysis of the actual rock samples, with instruments of sufficient power and sensitivity, can answer the question with the kind of certainty the question deserves. But here is what the evidence does currently support, and it is worth stating clearly. Mars, 3.5 billion years ago, had liquid water. It had complex organic chemistry. It had the chemical gradients and mineral environments that support microbial life on Earth. It preserved all of this inside rocks that are still accessible today. Everything that needs to be true for life to have existed on ancient Mars appears to have been true. The only thing we cannot yet confirm is whether it was. It is worth spending a moment on what the Mars sample return cancellation actually means in practical terms, because the political story and the science story are deeply tangled. The Perseverance rover is carrying sealed titanium sample tubes filled with drilled rock cores from some of the most scientifically valuable geological formations ever accessed on another planet. The Martian unit samples, collected from the ancient carbonate-rich shoreline of Jezero's lake, are considered scientifically priceless by the planetary science community because carbonate minerals are exceptional at preserving biosignatures, and because the Martian unit represents an environment that predates the river delta, pushing the timeline of habitable conditions on Mars further back than previously established. The Bright Angel and Masonic Temple samples, collected from the same region where the nickel and organic carbon were found together, are being considered as among the highest priority candidates for return. These samples exist. They are sealed. They are waiting. The science that could come from studying them in terrestrial laboratories, isotope analysis to determine whether the carbon is biologically fractionated, nanoscale imaging to look for cellular structures, amino acid detection to identify whether left-handed or right-handed molecules dominate, would be transformative. None of that science can happen until the samples come home. And right now, the mission to bring them home is in limbo. The irony is not lost on scientists that the most productive period of organic molecule discovery in Mars exploration history coincides with the period when the mission most needed to capitalize on those discoveries, Mars Sample Return, has lost its funding and its clear path forward. Every paper published, every biosignature detected, every chemical fingerprint found in a billion-year-old Martian rock strengthens the scientific case for returning those samples to Earth. But scientific cases alone do not fund space missions. That requires political will, budget allocation, and institutional commitment. And all three of those things are in shorter supply at NASA right now than the evidence for Mars habitability. The European Space Agency's Rosalind Franklin rover, which carries a drill capable of reaching deeper into Martian rock than anything Curiosity or Perseverance can access, potentially below the radiation-damaged surface layer where organic molecules are more likely to be intact, is now scheduled to launch in late 2028 after years of delays. It will carry a TMAH wet chemistry experiment, similar to the one Curiosity just used. It will land in a region called Oxia Planum, a vast clay-bearing plain that is estimated to be among the oldest accessible geological surfaces on Mars. It will drill, and it will look for exactly what Curiosity and Perseverance have been finding, but deeper in older rock, with more powerful instruments and a fresh set of chemical experiments designed specifically around what we have already learned. There's a line from Amy Williams, the lead scientist on the Curiosity organic molecule study, that should settle in the mind of anyone thinking carefully about what these discoveries mean. She said that we cannot yet say that Mars ever harbored life, but that the findings further support the evidence that Mars was a habitable world around the time that life on Earth originated. That single sentence contains everything important. Mars was habitable when life began on Earth. The chemistry that makes life possible was there. The water was there, the minerals were there. The organic molecules were there, and they have been sitting in the rock, waiting for 3.5 billion years until the right rover came along with the right experiment and found them. Whatever comes next, whether it is a sample return or Franklin's drill or some future mission we cannot yet imagine, the question that drives it all is no longer whether Mars could have supported life.